Hello, everyone, and thank you for joining us for this latest installment of the Lunchtime Lecture Series. If you're one of our regular viewers, it's great to have you back with us. And if you're joining us for the first time today, my name is Kristen Drouard. I'm the Secretary of the ITA's Committee on Education and Training, the ITASEC Committee, and I'm delighted to be hosting today's session, which has been organised by the ITASEC Foundation and notably by Michaela Daguzan from the Foundation, who, as usual, is behind the scenes with us today, helping out with the technical side of things. So a big thank you to Michaela for all her hard work. For today's session, we've teamed up with the ITA's Committee on New Technologies, ITATech, and we'll be taking a look at the design of fibre-reinforced segments. As always, at any time during today's presentations, you'll be able to put your questions to our speakers. To do so, you can use the question and answer box that you can see at the bottom of your screen. And at the end of all three presentations, we'll try to get through as many questions as possible. Please try to keep your questions clear and short. And if you remember to try and indicate the name of the speaker who your question is aimed at. With that, let's move straight on now to introducing today's first speaker, who is Dr. Veria Nasri. He'll be talking to us about the design and construction considerations for fibre-reinforced concrete segments. Dr. Nasri has a PhD in structural and geotechnical engineering and is currently Chief Tunnel Engineer and Senior Vice President at AECOM. He has more than 30 years proven geotechnical, structural, and tunneling engineering experience, including extensive geotechnical and structural analyses, as well as design and construction support for major tunneling projects. Dr. Nasri has published more than 240 journal and conference papers, mainly on the design and construction of tunnels and underground structures. So, Veria, if your camera and microphone are on, if you'd like to turn them on, then I'll hand the floor over to you.
Yeah, thanks a lot, Christine, for the introduction, longer than what I gave you. So, 1 second to share my slides. So, hello, everybody, and thanks for attending. So I am going to talk about a real-world example, and through that, try to explain some major details, give you an idea, and later you can go and read more on that subject. So I start with this example, which is a metro tunnel. So the conventional one-track 6-meter diameter. Here in this case, so if we talk about ring configuration, so either for this size, we are using 5+1 with a small key, or 6+0 with a big key, which it can be called also 4+2. All the segments, they are practically the same size. We define the segment length based on the alignment and minimum curve thickness. We try to optimize it even to the centimeter because that's a lot of material over kilometers. And then concrete use for this particular project is 50 MPa. Usually nowadays they use 60 MPa easily. That's typical. You see here the configuration for the tangent alignment, and also a small detail about the key segment draw with installation of the last element, which we have to play with the angles to have a draw which fits into the machine basically characteristic. Then for this project, we use universal ring, which is the best configuration with taper on both sides. For the taper, we use this simple formula. This formula, so you see here, phi A is outer diameter, bm is the length of the ring, and r is minimum alignment radius. We should reduce it by 20% for correction required for the alignment. Then I go to directly to the gasket design. So for this particular project, this is the water head we have, but we have to use a relaxation factor because this EDPM of material of the gasket, this with time, this soften and release the stress. So we have to use a factor of 2 there. So then we have to consider a gap and offset. You see it in this model for our design. So you see here the configuration when the gasket are not compressed and when they are completely compressed and joint is closed. Remember this number 12 when the gasket are completely open. So here you see here, and this number 21, which the gasket are completely compressed. So if we apply that 5% gap, that will be 26 millimeter. We go into this curve of that particular gasket, which gives the between gap and the water pressure capacity of the gasket. So with that 26, we come over the curve of the offset, which we consider 10 here. And we define the capacity of this particular gasket as 14 bar, which is higher than 7.2 bar we have. It's a factor more than 1.67, which is normal factor of safety. Here, this kind of gasket, this material, so it loses the relaxes very fast at the first 5 minutes. So you see this 300 seconds. In this particular gasket, it loses already 25% of the pressure, which we need to consider. Then with this gasket, we have to design the segment for spalling for this shear failure here. So this gasket material is uncompressible, and then when this is completely compressed, so then the pressure will be hydrostatic. It means the total...
Varia, excuse me, Varia, I'm interrupting. We have one participant who says he can't see the screen. Could the other participants just confirm that they can see the screen, please? I can, but could we just have a confirmation?
Kirsten, I can see the screen.
You can see the screen.
Yeah, I can see the screen.
Okay. Yeah, okay. Sorry to interrupt you,
Yeah,
Varia. I just wanted to check. Sorry about that.
I just received another response that they can, so there is no issue.
Excuse me, Varia, sorry.
No problem. Then we divide the pressure, the force we have here from the gasket divided by this, the length B, that it gives us the pressure. Then we apply it with the height here, that HS, and that would be the total load, which this should be resisted by this shear of this edge of the segment. And based on that, we design the geometry for the gasket. Now we go to the issue related to gasket, but for the design of the dowel in circumferential joint. So one loading which govern is accidental removal of truss jack for the lack of power or any other reason. So you see here the free body diagram, the weight of the segment, the force of the gasket, and the resisting force of the dowel here. So we take a moment around this pivot point, which is this edge of the stress relief area. This is the moment, and based on that, we can find basically the forces in the dowel and to see which dowel we can use for the design. Now we can go a little bit farther with a particular dowel. For this is dowel pull-out test results. So at yield, so this move about 7.7 millimeter. So if we consider the movement around the same pivot point, so with this 7.7, so the movement around the gasket will be 8.9. You saw, I show you that we had 12 millimeter, which the gasket was completely open. So the difference between two is 3.1 millimeter, which we go to the load deflection curve of the gasket. We find out that we have 12.4 kilonewton in the gasket, which will be used for the design to verify whether we have a stable situation here. So to design the bolts, this is very straightforward. The pressure in the gasket, So we have to consider two angles, one angle of the longitudinal joint and also angle of the point, and the formula we see on the side. So this will give you the design of the bolt based on the characteristic of the bolt. Now, we start the fiber concrete, the design philosophy. So we have to use the stress strain, basically a constitutive relationship from these ACI documents. And this we have to consider constant post-cracking behavior. We use usually a standard test like ASTM or EN to determine the post-crack residual tensile strength. And then you see these tests, for example, beam test, where we apply the load and we measure the crack opening and we draw this curve. So for this, first at FR1, when the crack is open 0.5 millimeter, that we use that residual strength for SLS. And when the crack is open 2.5 millimeter, we use that parameter FR3 for ULS. And then here, this is a different time. The strengths are different. Obviously, stripping is about 4 to 6 hours and 28 days. So you see in this particular case, which kind of numbers we have. And then this is the model I was talking about. So we said our concrete was 50 MPa. So the model for compression, so it's linear to 50 and then constant. The model for tension, so we consider, say, about 10% of the compression. Now it can be even 12% with the fiber. So that's 5 MPa. So linear, then we have a drop, and then it plateaus. So how we can find these things, either from the mixes based on our experience or using this ACI 5448R, then it tells you how you back calculate and build these models from the test result. And based on this data, we can build our P and M interaction diagram. This is explained in Appendix A of 5447R ACI. So now, how we design our mix. So if we have a number defined for residual strength, say FR3 at, say in this case, 4.6, but we have to consider a higher number as the mean result of the test to, with 95% on confidence, get this number. What we do, we use this formula, that mean. This is the specified value we have. This Kn is a coefficient depending on the number of the test. For example, here we are using 12, so the Kn is 171. And Vx is a coefficient of variation, which usually at the beginning we use 20%. So you see here, based on these numbers, so for a 4.6 FR3, our average mix result should be 7. So this is how we design the mix. So now we go to the advantages of fiber. So you are all familiar with is better ductility, less crack fit, better impact and spalling behavior, less steel and less labor to put these steels together, less space, workshop for the steel, and then less cost and schedule, better durability. Since we don't have rebar, so we don't have carbonation, chloride, and straight current corrosion, and less carbon. So what we use now for load cases and load combination, we use this kind of information from ACI for different load cases. This is the basic load cases for production and transient. You see the very simple model, either cantilever or simple beam. These parameters ASL, this is defined by the engineer, and the eccentricity is 10 centimeter, either outside or inside from ACI. For the moving load cases, so we use a impact factor of 2, and these are the simple model moments. You can define it yourself. For each of these equipment, you will have your free body diagram and the relevant moment for it. You see for this particular example how those are belts. And then in terms of the demand and for SLS and ULS, so based on FR1 and FR3, so you see for ULS, we are using load factor and strength reduction factor. So these are typical. And some small discussion about truss jack force. So for this particular example, David will talk about more detail this subject. So we use this iron guard diagram, which is analytical. This formula here is drawn. Here you see that the section in the radial direction. So we have here intrinsic eccentricity because of the presence of the gasket. And we have to consider a construction eccentricity based on ACI, say 30 millimeter on both sides of this. And based on that, we do the calculation. We can have dispersing in both direction, in circumferential direction also. You see here the configuration of the pads. So we have to design the size of this, but this should not be closer than 120 millimeter to the edge of the segment. And then we go to the spalling now. We don't have an analytical formula for spalling, so we have to do 3D analysis. We have to do a nonlinear analysis, and we have to verify the cracking. So in this particular case, we use total strength crack constitutive model. There are different constitutive model for cracking based on a smeared model. So, and then we consider different segment and different eccentricities. And for boundary condition, we consider normal compression only boundaries. So here you see the allowable cracking from 0.2 to 0.3 from the Austrian Towing Association, depending on type of the application and level of dryness. So for the spalling, as I said, in longitudinal joint, you see here, either we have this kind of trapezoidal or triangular distribution when the joint is open, when the resultant of the load is outside 1/3 middle of the segment. You see here, for this particular case, we draw the crack width based on the thrust force. This is the region which is not acceptable, is beyond the values which are specified. So you see the spalling stresses between the pads and the cracking, the result of the modeling. So then we get to tail skin backfill grouting. Nowadays, 2-component grouting is used, which at the beginning, so is liquid, then it mixes in a few seconds gel, and then over, say, 25 minutes gets to 1 kPa, and 1 hour about 100 kPa. So then we use this formula to solve for pressure of the grout minus pressure of the water, how much it should be more. And then we use the equilibrium in vertical direction based on weight of the liner, buoyancy of the grout, and then shear stress of the grout. And we find the unit weight of the grout, and based on that, we find the grout pressure gradient. And from that, we use this model of the ring of that pressure and its variation applied. So we use the interface between segment and also ground boundary, depending on if it's rock or if it's soil and how flexible it is. So different model can be used. And we get axial and bending and check it with the interaction. Now, if we have also, if we have deficiency in primary grouting, so we do secondary grouting. This is pressure applied on a limited area. But in this case, the primary grouting is already hardened. We should consider its parameter in the analysis. So in general, when we do the 3D modeling, we need to consider the shape of the segment, rhomboidal. Now, that's the best practice with tapered joints. And we need to consider nonlinear, basically constitutive model for FRC. We use Johnson nonlinear line interface for the joint. We use sequential excavation modeling, and we apply phase pressure and its variability. we consider conical shape of the shield and using gap element, and then gap element, and then we use the growth pressure considering the age of it and the strength of it. So one load case also longitudinal joint bursting. So for this one, either we use simplified equation from ACI or we use a 2D finite element. So this is very simple. We use a model here, which is twice longer than the length of the segment. And with that, so I get to the carbon. So with fiber, our carbon significantly reduces, because you see, if we use fiber instead rebar, we will have about half of steel weight, and then CO2 equivalent factor for fiber is less than half of the steel. So using fiber instead of steel, we are saving carbon by 5 times. Here you see the comparison. Here also we use some SCM, supplementary cementitious material like slag and also silica fume to reduce the carbon from concrete also. So for the references, you can use this document, 2 ACI documents, one for fiber, another one general, and the middle one ATI, which we contributed to producing this, and also a handbook which cover everything I said in detail and many other subjects. This is a good reference. And so the conclusion is, so the fiber is really the way to go. The rebar is obsolete for the segment. So it has significant advantages. I don't repeat it here. And through a example, so I explained some details of the design, which you need to follow up with the books and other references. And also the document I said, these are the guidelines, but this is a basically advancing technology. The things are moving very fast, and this needs to be updated with time. This is some other references. You can basically consider looking at them. And with that, thank you very much. So I hope Kristen and somehow on time.
Thank you very much, Feria. Thank you. Yeah, thanks for sticking to the allotted time. That was great. Thank you very much. Time now to move on straight to today's second speaker. Before that, just a quick reminder for our participants, if you have any questions for Dr. Nasri, please don't hesitate to type them into the question and answer box that you can see on your screen, and we'll try to get through as many questions as possible at the end of today's presentations. So our next speaker, Dr. David Oliveira, will be talking to us about the design of fibre reinforced segments against concrete bursting and splitting. Dr. Oliveira has over 25 years experience in civil engineering and is the technical director of tunneling with Oricon. He's also the vice animator of the ITA's working group 12 on sprayed concrete, and within this group contributed to the ITA guide on low carbon concrete tunnel linings. David is also a researcher or lecturer at several universities in Australia. So, David, if you'd like to share your presentation, then we'll hand over to you, and the floor is yours.
Thank you. Well, hang on. I'm not sure if I'm showing the right one.
You just need to go. Oh, take your time.
Yeah, I'll just just give me a second. Sorry. Okay. Can you see the presentation now?
Yeah, we can. You just need to go into slideshare
presentation
mode.
Yeah. All right. Okay. Well, thanks everyone, and good morning or good afternoon, good evening, depending on the time zone you are. Thanks for attending and listening to me. I chose this topic, and very briefly touched on a bit of this. I selected this topic because there is generally a lack of detailed guidelines when it comes to designing for bursting and splitting using fiber reinforcement. In a lot of the guides that Varia showed, you're going to find some recommendations on how to estimate the splitting forces and how to design, in the case we are predicting splitting, in how to design the conventional concrete reinforcement, but how to use fibers generally is something that we find difficulty in finding detailed guidance. So I thought that, it was a good idea to share my own experience here. So it's not the experience of ITA. And here, maybe at the question and answer section, what others have to say. I'm very pleased to say, though, that although this is my own experience, that the ITA Working Group 2 has also prepared a comprehensive guideline on this. I'm not part of that group. I haven't been involved, so I'm very much looking forward because we do need that. And I know some of the people working, I know they are very knowledgeable, and certainly it will contribute a lot. So hopefully what I'm presenting here is consistent with what they're saying, because this is based on my own sort of literature research and some of the experimental work I have done in the past. So I very briefly introduce what the problem is. What we typically do as practitioners, as engineers designing our segmental lining, how do we see fibers working in this particular failure mechanism, and present some of the previous studies and research done by a couple of groups, particularly from Italy. And I'm going to present one case that I was involved, which is a Sydney Metro case, how we assess these and how we move forward using fiber reinforcement only and avoiding conventional reinforcement. We all know what a segmental lining is. I call it the concrete Lego. It's just a series of pieces of concrete that are put together in almost like a Lego assembly type. And the way these segments interact is via joints. So within two rings, they interact via the circumferential joints, and between each segment, they interact via the longitudinal joints, as you can see in the picture here. I'll just put my pointer. So here's the longitudinal joint, also called radial joint, which I prefer to use the term longitudinal joint. So that's how they interact. Once this ring, so this segmental line is put under loading conditions, they will deform and they will cause compression forces and bending moments. And these bending moments will, of course, put the individual segments in flexion, so put bending moments in the segments. And this will also generate rotation about the joints. As you can clearly see here in this particular numerical model of one of our designs, just as an example here, that there's a tendency for the joints to rotate. So here, the joints have been explicitly modeled, as you can see here, this rhomboidal type arrangement as Veya showed before. You can clearly see rotation happening here, besides the exaggerated bending that happens here. So they locally rotate, and the way that the forces are transferred from one segment to the other is by simple concrete to concrete contact. And these forces are transferred via compressive forces, which, at this contact, they will typically have a certain distribution, depending if the joint is open or closed, as Veya mentioned. And this force will generate some compression right at the top of the joint, and eventually they will generate internal tensile stresses that can cause bursting in that region and can cause bearing failure at the top of the joint. So this is the typical thing we'll have to design against. In general, we can actually summarize the design, and I'll particularly focus here on longitudinal joints, although a few of the things here are also applicable for circumferential joints. We can put this process into a two-part process. The first component is to assess how the joints will behave, how they will deform, and how the joints will rotate and generate a particular contact stress distribution. The second step is to assess, once you know that contact stresses, is how we can design the segments to resist those stresses and not fail in bearing and in tension. So this is the second point here is the focus of this presentation. The first topic here is something that, as far as I understand, it will be very comprehensively addressed by this future ITA working group guideline, which I believe is soon to be published. I'm also very keen to give it a full read because I haven't been involved. So what I'm going to focus here, particularly because we are interested in the effect of fibers and how we can better use fibers, as Veya showed, very important to reduce carbon footprint and reduce costs and a series of other benefits. How we can use fibers to address this particular failure mechanism. So typically, in practical design, the thing we first do as designers, and they also touch this, is once we know the rotation and the applicable eccentricity, and we can identify what sort of contact stress distribution, which we typically find an equivalent rectangular, we define an equivalent rectangular distribution, we can estimate the distribution of stresses inside the segment below the joint contact here. And generally, we start with a linear elastic solution. So they also show numerical modeling is one that is very used. So finite element analysis to define the stress distribution, and the solution by Iyengar from 1962, which we show on the right-hand side here. Once we know this distribution, we know the compression zone here, we know the tensile zone, and we look at the peak tensile stress that develop here. It's not the average. We look at the peak tensile stress here and a maximum credible load, because we are concerned that this could cause a brittle failure. So we look at this maximum value here, and we compare to the tensile capacity, the design capacity of the concrete, which is, is the characteristic strength of the tensile characteristic strength multiplied by a reduction factor or divided by a reduction factor, which is typically estimated or tested under tensile splitting tests, or the so-called Brazilian tests. If this maximum or peak tensile stress here is less than that capacity, the design capacity, then we generally deem okay, and we do not introduce additional reinforcement for the joints. We just use the reinforcement that's required for the overall performance of the segments, either with conventional reinforcement we're using, or fibers. If the peak stress does exceed the tensile capacity of the concrete, the design capacity of the concrete, the very typical approach is to initially, one of the most common approaches, to generally introduce at least some local joint reinforcement, which you can see here in these pictures here. So by this sketch here and a photo on the right-hand side. And this type of reinforcement is very well addressed by all the guides that Veria showed, the ACI guide, the ITA guide, the DAUB, and a few others, because this comes from conventional concrete design. We use strut and tie models. We find the equilibrium of forces here. We can identify what is the tie force that we need to introduce with the reinforcement to resist this. However, this is not necessarily applicable for fiber reinforced concrete, because this is based on compatibility of forces or equilibrium of forces, and not necessarily compatibility of deformations and strains and stress. So a few people looked at, okay, how can we then do for conventional, well, so for fiber reinforced concrete? And here I present some of the work done by one of the groups from Italy, Trabucchi, into 2022, but he was discussing an earlier model from Schnutken and Erden from 2001. So this is as early as I'm aware. There might be others, but Schnutken and Erden, what they introduced, they still adopted some linear elastic concepts and limited the distribution of stresses under that, highly concentrated forces on the joints, limited to a disturbed region or discontinuity region, as we call here, that is similar to those estimated by linear elastic solution. The only difference is that they suggested that we could use the residual flexural strength here, corrected or converted to an equivalent axial tensile resistance. And then Trabucchi, based on this model here, presented here an estimate of the maximal force that we could apply for this joint based on Schnutken, and could be calculated by this equation here, with this being a residual flexural strength that's corrected or converted to an equivalent axial tensile axial strength. Also, continuing with these studies, actually even earlier that Trabucchi in 2022, there's other works also by a few other Italians, Tiberti and Conforti. They all studied, how we can better understand the failure under high concentrated loads and splitting, particularly splitting when we're using fibers. And what they observe is that the failure mechanism did quite substantial experimental work and tested a number of samples where they loaded, and they observed that there's generally three phases of the fiber reinforced concrete under these highly concentrated loads. We have a first phase where the concrete remains relatively elastic, and up to a point where you get the first splitting cracks. crack. So if you have an unreinforced concrete, you have your brittle failure. But if you have your fiber reinforced concrete, and you see here in particular steel fiber reinforced concrete here, you have a hardening process here because the crack starts to develop, and because of the increasing length, you start to gain some resistance from that splitting crack up to a peak value, where beyond that stage 2, which is the peak value, you develop this compressive cone wedge failure, and then you get your total failure. One of the things that all these studies observed is that the cracks that are relevant for the design are small cracks, generally always less than 1 millimeter. So we have to put focus, and that's one of the messages of these studies, that we have to put focus on the smaller crack with resistance or the flexural. In this particular case here, is the way we typically test is by testing the residual flexural strength at lower or serviceability limit states that we generally refer to, but it's more focusing on smaller crack widths in the order of 0.5 for the crack mouth opening. And because of that, it's something, when you're looking at our mixed design, we need to look very careful, because we are looking at this small crack width. We need to focus on, a good fiber network, which means the amount or length of total length of fiber within a volume of concrete. We have to target that these fibers have good bond and very good stiffness to early mobilize their strength in small cracks, which generally leads for us to have a better performance using steel fibers, because macrosynthetics, for example, will require a lot more deformation to mobilize ultimate capacity, and they generally won't provide that sort of low, small crack width resistance. So, with this in mind, we started looking at our design. I'll present here this particular study case from Sydney Metro. We did the typical thing here. Is a typical metro tunnel, so internal diameter in terms of 6 meters. Our segment was 260 millimeters in thickness, and we estimated a credible maximum load that would be in the order of 4 meganewtons or 4,000 kilonewtons per meter, with a certain eccentricity, which was based on numerical modeling and some accommodation of tolerances for construction. So using that typical approach, we estimated peaks bursting stress, which is in the order of 7 MPa, which we identified that was exceeding our tensile design capacity. Therefore, we would be going beyond the elastic limit into the cracking zone. And that's where now the guidelines stop working, because that's the only recommendation that we have here for up to this point, linear elastic, or if we start introducing conventional reinforcement, which is something that we didn't want to. So now we started investigating. At that time, this was circa 2021, maybe going to 2022. We look at that model by Schnutken from 2001, which is an earlier model. But one of the things we realized, again, it's still based in that elastic assumption that it's limited to the disturbed zone, which is similar to the linear elastic assumptions. Using that equation with mean value of FR1. I'm using mean value here because when it comes to non-elastic or non-linear behavior, most codes will allow you to use mean values if you do full numerical analysis, which we're going to do later. I'm going to show it to you, but I'm just for comparison purposes, I'm using mean value here. We estimate only about using the fibers with that mixed design. We'd only achieve about 2 meganewtons. And this is ignore eccentricity. If we introduce eccentricity, we'd only estimate 1.7 meganewtons per meter, which is well below what we needed. And this is not even putting a factor of safety here or a reduction factor. We weren't quite satisfied with this, so we started looking in how can we improve this. The first thing we look at is our segment design. First thing we looked at, we were originally adopting a 50 MPa, like Varia showed as well. But the contractor was already specifying for his segment a much higher concrete strength, not because we told them that would be needed, but because he wanted to be demolding very quickly. He was targeting to produce one segment every 4 minutes, and therefore he was using a much higher concrete strength with a characteristic value of 65 MPa and mean value in the order of 75. When we got that information, so we might as well use it. If we have that strength, we might as well take advantage of it and not just throw it, in the bin. And that allows also to have a slightly higher tensile splitting strength, which can start use. And one thing we proposed was to changed the steel fiber that was being used to a higher performance one, which we decided to adopt the drum mix type fiber here, 8060, because it's a high tensile strength. It has a low diameter and would provide a good fiber network, a good amount of kilometers of fibers per cubic meter. And with that, we targeted and we achieved a strain hardening flexural behavior, which would give us a very small direct tensile softening from the first cracking to the C mode 1, the 0.5 millimeter crack mouth opening, which is more or less equivalent to a crack opening displacement. So one thing here is the crack mouth opening in flexure, and the other one is the crack opening displacement in direct tensile here. So the crack mouth opening 0.5 in flexure would be in direct tension, more or less equivalent to a 0.2 millimeters. It would provide a small strength softening within that first region, but right after that 0.2 millimeters COD, it would start hardening again because we were achieving in our mix ULS values, so FR3 and FR4s that were greater than the equivalent axial tensile strength stress estimated from the flexural results. So we are happy that we are achieving a very good performance mix, and we decided to also go beyond the linear elastic assumptions, and we do a full non-linear analysis using more sophisticated concrete modeling based on fracture mechanics, and we used severe crack models with some additions that could allow for biaxial enhancement, and we used Athena concrete software as our tool, and we base our concrete modeling in all the recommendations that exist in the FIB model code 2020. So here are some of the constitutive equations and graphs that you can find in more details in the FIB model code. The first step we did to be confident that our modeling technique was able to represent real cases and particular experimental work, we simulated some of the tests done by Conforti in 2016. And we showed that, using, of course, their concrete properties, we could fully represent with, that type of modeling technique what was happening with the test results, both in terms of load and crack opening, but also in terms of crack development and failure mechanism. You can see here the cone failure, the development of the splitting crack in the moment. And this gave us some confidence that we're in the right track. And we started simulating our joint rotation numerically as well. And what we observed is by doing nonlinear stress modeling with proper fracture mechanics, we were predicting much higher capacity than those empirical application by Snutgen, and also, of course, by what we were originally limited in terms of linear strength analysis. So we were achieving unfactored values here in the order of the 6,000 kilonewtons per meter, 6 meganewtons. So of course, when we start getting this sort of, wow, this is really good to be true, we started investigating a bit further. And at the same time, we were lucky to find that there was this, the work by Trabucchi, almost happening parallel to what we were doing. That was demonstrating that model by Snutgen and Nerden was generally under-predicting severely their experimental work. So you can see here, it was under-predicting by 2 to 5 times. And what they did is they also proposed a different equation that would take into account that, considering non-linear behavior and that the crack needs to develop perhaps a bit longer than just the conventional disturbed region, generally from 1.5 to 2.7 times, as long as the crack width is maintained small, generally, always less than 1, but generally in the order of 0.5, 0.6 millimeters, they could achieve a higher result. And they propose this other semi-empirical equation here that we decided to investigate too. But not only investigate this, we would investigate this with our own experimental work. So we could make use of what the FIB model code mentions as verification assisted by testing. So we produce samples of our segment joint here. Of course, not the full 1 meter, it was limited to the same thickness, to the same length of the thickness, but we introduced very high concentrated loads here. So you can see here the loads were applied only in this red zone here, only 50 mil. So the joint is very small joint, only 130. And we applied the loads with very high eccentricity to understand how this joint sample would perform in terms of these highly concentrated loads. And what we observed here is that They achieved for the 260 millimeters length, they achieved something that was in the order of 1.6 meganewtons. So this is not 1 meter. You see later that once we multiply this by the 1 meter, we will get very close to what we were needing. Unfortunately, our compression machine that we're using wasn't displacement control, so it was only picking up to the peak load, and we were missing out on the post-peak behavior, which we picked with our own numerical model to try to recalibrate the original predictions we had in design. And we were quite satisfied that, again, our model were representing very well what we observed in these tests. Now, comparing what the model by Trabucchi would predict for these tests was very actually pleasantly surprised that the semi-empirical model by Trabucchi would predict in the order of 16-20 kilonewtons, while the test, if you remember, was about 16 kilonewtons. But there was interesting aspect here. We would only achieve this prediction if we are using the full thickness and not necessarily the effective thickness that's governed by the eccentricity, which might be indicating that for fiber reinforced concrete, the distribution of stresses may be beyond that limited effective thickness and might spread, might engage a bit more. So using that, it would predict in the same values. So if we extrapolate those test results, we would achieve that 6 kilonewtons. If we extrapolate the Trabucchi, it would estimate that also achieve that 4 meganewtons. And what we did is, because we recalibrated our own model, we rerun the models with the recalibrated parameters, and we put here the two to compare. So our original prediction was already pretty good. So the difference here were very minor. There was only a minor increase after we recalibrated. And again, the recalibration that indicated that we could achieve the capacity that we needed. So when we added all of this together, it gave us some confidence that particularly considering that we were using quite a high load, which although credible was quite unlikely to happen, that we didn't need to introduce conventional reinforcement, and we could use fiber reinforcement only in the segment. So the segment designed for Sydney Metro, that particular section is entirely fiber reinforced only. So my final remarks is that the design of longitudinal joints against bursting splitting still lacks good design guidance, and I think this ITA guideline is soon to be published will shed some light, and I think we are all expecting this. I'm sure it'll be fantastic work, and we'll address a lot more than what I have talked here, particularly on the first bullet point that I mentioned before. The use of linear elastic assumptions generally won't give us the full benefit of fiber reinforced concrete behavior, and may limit its benefit as a solution. And we have to go to nonlinear modeling, which is essentially what I'm discussing here in the third bullet point, with some promising results by the semi-empirical model by Trabucchi from 2022. In this particular case that I presented to you here, we demonstrated the capacity would be 3 to 3.5 times greater than what the linear elastic solution would predict. And we are quite satisfied with this, and the results were consistent with other studies. And that's it for today. Thank you very much for your attention.
Thank you very much, David, for that insightful presentation there on the mitigation of concrete bursting and splitting, with an interesting case study from the Sydney Metro. Time now for our last presentation, which will be given by Charles Allen. Charles will be talking to us about the steel fibre segmental lining and other innovations in the Lee Tunnel project. Charles is a leading specialist in concrete engineering and construction materials with over 45 years' experience. His experience includes the use of concrete for civil, building and tunnelling applications. After a number of years working in the construction chemicals industry, he was appointed Managing Director of the International Centre for Geotechnics and Underground Construction based in Zurich, which is a foundation responsible for the training and qualification of staff for tunnelling projects. More recently, Charles has been involved as a consultant to a number of different organisations within the civil engineering and tunnelling sectors, and has recently been advising contractors in projects in Singapore, New Zealand, Australia and the UK. So Charles, if you'd like to switch on your camera and microphone, then we can hand over to you. The floor's yours, Charles.
Thanks, Christine. I shall start sharing my slides. Oops. Good afternoon, everybody. I'm going to talk about a project I was very much involved with for probably about an 8-year period, which was the Lee Tunnel project in London, which commenced construction in 2010 and completed in 2016. Now, the Lee Tunnel is this section here. Let me just move this out the way. The Lee Tunnel is this section here. It was the first part of the Thames Tideway project. The Thames Tideway project was a very long tunnel. It's just been completed last year under the River Thames to collect combined sewer outfalls along the river and deliver them to Abbey Mills pumping station, and then from Abbey Mills pumping station to the Beckton sewage treatment plant. And this was the Lee Tunnel, and it was 6.9 kilometers long. Won't move.
Are you having trouble moving your slides forward, Charles?
Yeah, yeah.
Could you try maybe the cursors, the arrows on your keyboard?
I'm trying. That's what I'm trying to do.
What about your mouse?
I don't have a mouse.
Okay.
Oh, that's it. There's a
It's
curve.
going. Maybe
Bottom
there's
left.
a slight delay.
Yeah, okay, there's no problem. Right, the Lee Tunnel, there's Beckton sewage treatment works down here, where we had 3 of the deepest shafts ever constructed in London. The largest was the 38-meter diameter shaft, 86 meters deep. And then at Abbey Mills, we had another shaft. In fact, we built 2 shafts at Abbey Mills because we had to have a reception shaft for the TBMs from the Tideway project. Basically, tunnel 98 meters deep at one end, and I think 83 meters at the other end. And the total length of tunnel was about 6.9 kilometers. The project value, when the contract was signed, was 635 million. It was built by Thames Water. Project manager was CH2M Hill, and I was a consultant to CH2M Hill on this project. Design and build contractor was a joint venture between Morgan Sindall, Vonsi, and Bashi Solitanche, and the segmental lining manufacturer was Morgan Sindall. Tunnel length 6.9 kilometers, internal diameter 7.2. That included a secondary lining 300 millimeters thick. So the primary lining was 7.8 millimeter internal diameter steel fibre reinforced universal ring with, just a minute, with 21 millimeters taper, 350 millimeters thick, and it was comprised of 7 units plus a key. We had a few innovations on the project. We used convex radial joints. It was at the time, it was the largest diameter steel fibre reinforced segmental lining project in the UK. We had cast-in EDPM gaskets. We were only the 2nd major project in the world to use cast-in gaskets. Couple of innovations we also had was the 3D laser checking of segments as routine quality control, and we had a concrete maturity monitoring system to control strength development and thermal shock. The convex radial joints, they eliminate the crushing of segments when bird mouthing occurs, and David spoke about this earlier in his lecture. And it maintains a continuous line of contact and eliminates eccentric loading due to poor ring building. So you have always have an actual load. The radial joints, we cast some full-size units of concrete with curved radial joints with a radius of 2.5 meters on the joint, and we did extensive full-scale testing at the Building Research Institute, building research establishment at Watford in London, and we decided to adapt the curved joints, which actually meant us changing the specification because the original specification had gasket grooves, and we were using cast-in gaskets, and the radial plane on the radial joints. So we changed the gasket from grooves to protrusions, and the radial convex faces plus or minus 10 millimeters on design radius. And how we came up with this, because the sensible thing we did was we spoke to the mold manufacturer and asked him what sort of tolerances he could achieve, and then we adopted that in our specification. The steel fibre reinforcement, we only used 30 kilos of Dramix 8060 BN steel fibres. We used 1 kilo of Adfil monofilament polypropylene fibres. This was to eliminate the risk of spalling in accidental fires during construction. Obviously, we were not subject to road or rail fire curves. And the characteristic flexural strength was not less than 2.2, and the characteristic tensile split strength was not less than 3.3. Obviously, one of the first things we did during initial production was to break a couple of segments in half and look at the fibre distribution, which was very good. And so we didn't have to do that anymore. We used cast-in gaskets, and I'd say we were only the second major project in the world to use cast-in gaskets. We used the Phoenix Tokyo M385 gasket. Recesses were machined into mould walls to seat the gasket. The gasket was cast into the segment, and at the time we were the largest project in the world to use cast-in gaskets. The benefits of the cast-in gasket in production are you eliminate the gluing station and associated labour. There's no requirement for a gasket clamp. You get better seating of the gaskets, and there's no health and safety problems with solvented glue in a factory or site location. Installing the gaskets was quite a simple operation done on the carousel production line, and we checked them we came up with basically a mirror on a stick, like the sort of thing that dentists use when they're looking at your teeth. And those were the finished segments, and the benefit was we got perfectly seated corners that you don't always get with glued gaskets. We specified, and I actually drafted the specification for the segments for this project, specified the 3D laser checking of segments using a 3D cloud system. The benefit of this is the finished article is checked and not the mould. There are less interruptions in production because you don't have to withdraw the mould from the carousel for routine checking. Checking of a segment takes approximately 15 minutes, and we checked 5% of production routinely, and it gave a much greater accuracy of measurement than calipers and gauges, which is important when you're using a universal ring, which doesn't have a baseline edge that you can measure from. And we set trigger levels that, if exceeded, the mould would be removed from the carousel and the mould checked and re-engineered if necessary. So this was the setup for 3D laser checking. You have 2 laser stations recording there, and the man goes round with the machine with a little mirror ball, and he moves the mirror ball over the edges of the segment, and then you can check dimensions. It's all fed into the computer. The system we use was supplied by VMT from Germany, and the segment producer was he was a bit reluctant to use this at first, but once he got used to it, he was very much in love with it, and he used it for all his subsequent projects after that. We also incorporated maturity monitoring for the checking of early age segment concrete strength by maturity monitoring, and we also specified that in the works information. And the benefits are the actual concrete strength in the segment is known at demolding stage. You're not trying to crack a cube. You're not trying to crack a cube and compare it to your in situ strength, because the cube strength will always be lower than the strength of the concrete in the mold. You get less damage to segments at demolding, handling and stacking, and curing chambers temperatures can be reduced, which gives you energy savings in the production of the segments. They used concrete maturity system called the START system, strength assessment in real time. And this works on having thermocouples inserted in the concrete, and then you have a little transmitter, radio transmitter. This was housed in a plastic case, and that transmits the signal, which is temperature and time at 10-minute intervals, and that goes into a data logger in the segment factory office, and from that you can download strength and temperature. Here you can see the temperature. This is when the concrete's cast. It goes into the curing chamber. This is the middle of the segment. This was the surface of the segment, and unfortunately there seemed to be a transmission problem here, but generally speaking you can see it comes out of the carousel and the temperature drops. Using this system, you can actually measure the in situ strength of the concrete. Here the concrete was cast approximately 7 o'clock in the morning, and at 6 hours later, when it was demolded, it had you can see its strength. We required 11 MPa lifting strength, and you can see the average strength in the segment was 15. So by placing the maturity monitor into the last segment of each shift, you can determine what your strength is. Also in the specification, and you often see this in specifications around the world, and generally it's a copy and paste from the previous job. The storage of segments for 24 hours within the factory to mitigate against possible thermal shock was specified. So when the compressive strength required for demolding is attained, allow the segments to cool. Segments shall be pre-stored internally within the casting factory for a minimum of 24 hours after demolding. The issue with that was we had a relatively small factory, and to store 24 hours of production inside the factory was really taking the factory to its limits. So it was suggested to the manufacturer that by using the maturity monitoring system to measure internal temperatures and surface temperatures and the ambient temperatures, they might be able to prove that 24 hours internal storage was not necessary. So we changed the specification to allow proposed control processes that will be submitted to the project manager for acceptance prior to implementation and reviewed appropriately with consideration to seasonal temperature variations. So what we did, they set up on a segment. This is the segment in the carousel, and we had thermocouples at the midpoint of the segment and the actual surface of the segment, and these were above and below. So these were ambient temperatures. Obviously, the temperature above the segment in fresh air was more than the below because heat rises. And the critical thing is this temperature differential between the segment center and the surface of the segment. Now, traditional thinking is that you take the temperature at the center of the segment and compare it with ambient temperature. Well, because of the heat flux coming out of the segments, the actual surface of the segment never actually gets to ambient temperature for at least 24, 36 hours after demolding. So we proved that this temperature differential, which was only maximum about 15 degrees, was totally acceptable and within specification limits. And so we allowed the precaster to actually move the segments to outdoor storage, even in the winter. And because we proved that there was no real threat of thermal shock in the segment. So to summarize, the use of steel fibre reinforced concrete in the largest diameter tunnel that had ever been used in the UK. And remember, we currently have about 30 years experience of steel fibre reinforced segments in the UK. The use of cast-in sealing gaskets, 3D laser checking and concrete maturity system enabled the segment manufacturer to improve productivity, reduce labour, reduce energy costs. He could lower the temperature in his carousel curing chamber. It reduced segment defects. We had only less than 0.2% rejects after 13,000 castings, and it improved quality assurance, quality control procedures by not having to use cubes and getting them tested and then trying to compare them to the strength of the segment in the molds, because we knew what the actual segment strength was. So with that, I think I've finished, and I'll hand over to you, Kristen.
Thank you very much, Charles. Thank you for that very clear presentation. I'm sure that some of you have some questions for Charles, so don't hesitate to type them into the question and answer box. That was our last presentation today, so we're now going to move straight on to our question and answer session. And for that, I'd like to invite Veria and David to turn back on their camera and microphone, and then we can kick off. Thank you. We've had a lot of questions coming in today. We'll try to get through as many of them as possible. I'll start with the very first one, but I won't necessarily go through them in order. The first question right at the top, what is the recommended methodology for designing and selecting gaskets, capable of withstanding hydrostatic pressures exceeding 100 meters of waterhead in deep tunnel construction? I think that was a question for you, Veria.
Yeah, okay, good question. So this obviously high pressure, but the gasket have been designed for more than that pressure. It means these 10 bars. So now is relatively typical, this 100 meter of water. So If you look at literature, there have been cases designed for 15 or even slightly more than that bar. So the same procedure will follow, but then the type of the gasket should be designed for that. It means the shape of the gasket, the size of it, width of it, and also the whole configuration with the holes in the gasket. And there are typical standard tests, usually Stua from the German Institute for testing gasket, which can test the particular gasket for this kind of pressure. So that can be done. You can look at the chapter 7 of the book, explains all these things, or look at the guideline by Stua, then you will find all this. So there's no problem for designing a gasket for 10 bar.
Okay, thank you, Varia. I'm scrolling down now, and a first question for David. David, are there any structural design codes available to refer to for fiber reinforced concrete's improved post-cracking behavior?
I think the one that I like the most, and I mentioned these in my presentations, the FIB model code, of the 2010, and now the latest one, 2020, have chapters that detail that fiber reinforcement effect. There's other standards like Ryland T62, and there's other, not necessarily standards or codes, but there's also other guides like the Concrete Association TR63 guide. But if I am to suggest one, also have a good look at the FIB model code 2010. It's very good information there, complete.
Okay, thanks, David. First question now for Charles. Charles, while fixing gasket joint tolerance, have you considered tidal impact induced ring ovalization, in case of poor backfilling? And have you considered whether entrapped air risk was considered associated with gasket installation processes? Two questions in one there, but go ahead.
Yeah, in terms of the design, that was left to the tunnel designer to draft the tolerances. In terms of the production and entrapped air, I'm not quite sure where does the question mean entrapped air underneath the gasket or entrapped air adjacent to the gasket in the face of the joint? We really didn't have any problem with air voids under the gasket. We obviously can't check. We couldn't check if there were any air voids behind the gasket because it was the gasket was cast in. So that's the best answer I can give.
Okay, no, thanks a lot, Charles. Question just below that one here for Varia. Can you discuss, Varia, whether the design of sprayed fiber reinforced concrete segments can be fiber only at adits and cross passages?
Okay, that's a good question. So obviously it depends on the size of the opening, size of the adit. If it's a small adit, so say satisfying the NFPA 130 requirement for a subway job, like the tunnel I show you, yes, you can still go with the fiber only. So you can use the bicons. I didn't have enough time to show these details to basically create the shear strength between the rings. But if its opening is very large and you get high moments, then you need to use a hybrid. It means a combination of fiber and rebar. And the way to design it is that's also is explained in the chapter 3 of the handbook, and we have several papers on that particular subject to basically the model for designing hybrid segments. But in most cases, so you can go only with fiber.
Okay, thank you. A question here for David. David, did you carry out a cost comparison between sprayed fibre reinforced concrete and conventional segments in the case of the Sydney Metro?
We did some comparison, but it wasn't so much cost related. The contract, our mix design only had 30 kilos of fiber, so you wouldn't be able to just do 30 kilos of conventional reinforcement, and just by means of the minimum reinforcement. So it was always cheaper, and the contractor. The precast yard in particular, it has so much more benefits in the casting. So it has safety requirements. You don't have to get people, playing with the reinforcement cage and so on. So it wasn't really a need. So there was, full interest to always go fiber only where we could. Like Varia mentioned, there was. I'll just add to the previous answer. The only case where we had reinforcement in the segments were some of the cross-passage openings where we had very high loads and we were exposing the back of the segments. Because we had larger openings and we had to expose the back of the segments, and this would put a lot of more flexural. So there were cases where we had to use conventional reinforcement, but the 95 to 97% of the segment was fiber only reinforced, and it was more cost effective. Yeah.
Okay, thanks for clarifying that, David. Another question for Charles here towards the end of the questions. Charles, the inner lining layer of 300 millimeters is quite large, considering that the primary lining is made of 350 millimeter segments. Was it due to operational requirements?
Yes, it was. The reason the secondary lining was installed throughout the Lee tunnel and the Thames Tideway tunnels is that certainly the Lee tunnel is in a chalk aquifer where drinking water is extracted from in East London, and it was required by I think the Environmental Protection Agency that we had a double lining, a belt and braces. I mean, the tunnel would have stood up on it. Well, it did stand up on its own with segments only, but we had to put in the secondary lining as a belt and braces job to stop sewage entering the groundwater through the lining. In terms of 300 millimeter thickness, I think we had a nominal structural thickness of about 220. By the time you add on the construction tolerances, we ended up with a nominal 300 millimeter thick lining.
Okay, thanks, Charles. Thanks for answering that
That
one.
was an environmental issue, yeah.
Okay. Varia, another one here for you. When designing for secondary grouting, why is there no earth load involved?
My presentation was relatively short. I couldn't go through all those discussions. So then the ground is actually modeled. It means the finite element configuration I showed you. So we are modeling the ground also. That's ground depending on if it's rock or if it's soil. So if it's rock, so when you're considering the stiffness of the grout, so that will be like a rigid boundary. But if it's soil, we consider that boundary, that interface in the model. So the ground is already considered there. So this grouting is one load case. So obviously we have all this combination, and in the analysis, so we can consider the ground and water pressure also in the model. I wanted in that slide, I wanted to show these load cases for the primary and secondary grouting and what should be the consideration when modeling these elements.
Okay, thank you very much, Varia. David, another question for you here. How is the performance of fibre reinforced concrete tunnel segments against A, repetitive thrust cycles, and B, overjacking?
I'm not sure if I understand what the person means by overjacking. If it is the thrust forces, again, if it is the thrust forces you design for, bursting, splitting in a similar way. You just have to look at the different configuration, like Veria showed. Repetitive cycling is not something that I have particularly investigated. But I would assume that, like in any case, as long as as long as your magnitude of the cycle are not approaching, particularly the unstable cracking phase of the concrete, it will perform certainly better than conventional. I would say it would perform better than conventional reinforcement, because you have a matrix that's fully reinforced rather than localized by reinforcement. But this, of course, depends on the magnitude of your amplitude, or your amplitude of your cycles. But this is not something that I have deeply investigated or look at the research, so I can't answer that in completeness. But that's just an impression I share.
Okay, thank you, David. Charles, another question for you here. In the segments, PP fibres are added for fires during the construction. What was the maximum amount, and how was fire protection with traffic guaranteed in your case study?
We use 1 kilo of polypropylene fibres, less than 32 microns diameter. In terms of fire during construction, just the normal sort of safety measures. We didn't have a fire during construction, and for long-term use, fire resistance was not required because it was a stormwater overflow system, and so they were put in there really just as a safety net, if you like. Okay, 1 kilo. That's all we needed.
Okay, thanks, Charles. Scrolling down just below, Veria, one for you here. Concerning spalling stresses and crack widths between TBM thrust jack forces, is there a criteria or analytical equation to evaluate it in during design?
The simple response is no, as I explained it in the presentation. So we have analytical solutions for bursting, but not for spalling. So in the preliminary design, so based on your experience, you have to have a sufficient distance between jack pads, and obviously having a reasonable thickness for the segment. And then in the final design, you need to use those kind of 3D nonlinear finite element analysis, considering modeling also the crack using one of the available models, mainly based on a smeared crack model, which in this case, for example, we use total strain crack model. So, and with that, so you can evaluate the crack opening and compare it with the criteria of the guidelines, like the one which is very good in this field is the Austrian ones. So it's tell you based on application and based on dryness of the tunnel. So it gives you the 4 category from 0.2 to 0.3 millimeter crack opening.
Okay, thanks, Feria. I'm going back up now, try and find another question here for David. Keeps jumping around here a bit. David, could you comment on the safety model, the load and resistance factoring that you applied for your nonlinear model?
Yeah, here in Australia, we are now trying to recommend the use of PAS 8801. In general, is something that we have been suggesting to the authorities here. That one in particular, we followed something that was closer to the local Australian bridge code. So we had, I think, a load factor that was in the order of 1.5 and a reduction factor which was also in the order of 1.5. But what we have been using, for example, in our sort of most recent tunnel, for example, which is the Western Harbour tunnel, which is also is a large diameter fiber reinforced only segment, possibly the largest fiber reinforced segment in the world at this stage only. We are using PAS 8801 for those for in terms of load factors and reduction factors.
Okay, thank you very much. Next question for you, Charles. Do you have any percentage, any figures that you can give us of rejected casting in traditional reinforced segments with steel bars? In your presentation, you said that the percentage was less than 0.2% when fibers were used in concrete segments in your project, just for a comparison between the two different types of methods. Do you have any figures?
I don't have any. I really don't have any figures for traditional reinforcement. The great benefit of the steel fibers is you're actually reinforcing the concrete to its boundaries. You don't have a cover zone, which is weak. It's unreinforced, and a lot of it depends on the competence of the precast manufacturer, whether they keep knocking off corners and edges from traditional reinforced concrete, or if you're using steel fibers, as I say, the great benefit is you can knock the corner or an edge of a segment during handling, transport, stacking, etc. But you get much less damage.
Okay, thank you, Charles. Right, another question for Veria, scrolling through a bit here. I guess this one was for you, Veria. Why is the 2D modeled segment in the case of contact modeling twice the length of the real world model?
So that's again, since I probably explained that one too fast, so there was a misunderstanding. So what I said, that for the longitudinal joint, when modeling the bursting tensile stresses, so the model we are using is basically applying the load to one segment with the width of the segment or length of the segment, and with the other direction, the circumferential direction. So we consider twice the length of the segment to remove the boundary effect on the analysis. So that's what I meant, which was kind of misunderstood. So that was only the size of the model to basically eliminate the boundary effect.
Okay, thanks, Barry, for clarifying that. Thank you. David, was the potential effect of the guiding rod on the stresses distribution taken into account in your design, or is it assumed negligible?
No, if you recall the pictures, we modeled explicitly the guide rod pocket there in the joint rotation and how it was distributing. Also in the test, we also cast the joint exactly with the same tolerances and the same using a mold that was specifically made to replicate the actual segment a joint having the guide pocket. So in our models, we did consider the effect of the pocket, because that was also a concern that, because you had that void, potential void or a plastic type material in the middle that you could concentrate more stresses and it would affect the contact stress distribution. Which we captured in the numerical model because it was explicitly included.
Okay, one final one for Charles here. I'm not quite sure I understand, but you might understand better than me, Charles. Is the sorry, it's gone back up again. Lost the question. Lost the question now. No, while I'm trying to find that one, I'll have one final one for Veria. Veria, how do you overcome workability reduction due to fiber reinforced concrete?
Okay, so that obviously depends on your mix design, so and which kind of mixture and super plasticizer or other you are using in your mix design. But in certain cases, you may have a very low slump concrete with close to practically zero, but you overcome this by a good vibration of the segment. So you need to have a good mold design to be able to vibrate well and to be able to avoid the bug holes and when you have such a low slump. So, and then concerning the pumping and those things also, there are also ways to handle this. So even with very low slump, so there is no problem with workability of fiber concrete.
Okay, I've found the question for you, Charles. I'm still not quite sure I understand. Is the fiber reinforced concrete tunnel lining segments, are they taken care of for flotation criteria? Can you?
I really don't understand that question.
No, I'm sorry. I'll have to move on to another one, perhaps one for David, and then I'll ask you all to choose one final question that you can ask because we're coming to the end of our time. I think this one was for you, David, but I'm not no, perhaps not.
That's okay, we can try.
Okay, go on then. If the exposed fibers on the surface affect aesthetics, will they also affect durability? That's how I
You look
understood it anyway.
on precast segments, generally this is not a problem. I mean, you have steel mold and you have a good finish. You could have maybe at the top surface, but that's also generally finished by hand. What we generally do in terms of durability is we do in most cases allow for a fiber loss depth to account for certain durability issue if that is really real, which there's a lot of debates about corrosion of steel fibers, but we generally do assume 10, 15, 20. We have been using a lot recently, 20 millimeters of fiber loss. It's not section loss. You just bear with me. You pay attention to what I'm saying here. It's not, you don't lose the section, you lose the effect of the fiber in tensile capacity over 20 millimeters depth. And then by that, you are, taking care of that, longer term durability, in addition to all your mix design, having proper, cementitious, slag or fly ash that will improve your durability.
Okay, thanks, David. Right, now we're starting to run out of time, so I'm going to let each one of you choose one final question from the questions that you can see. Veria, I'll let you pick and choose one final question that you think is important that you'd like to answer.
But all the questions, they are important here.
Of course they are. It's not easy, but fortunately we're going to have to pick and choose here.
Choose the most important one here, but if I can respond generally, so there are the established methods for fiber concrete or fiber segment design now. So it means those guidelines from ACI, which now we are working on them to make them code, and that's in process, is significantly advanced, and soon will be published as code. So then what I presented, unfortunately, the time was limited. So all the requirement for determining the loading or the requirement for the analysis, these are well established now in the industry, and then fiber segment became the default. Obviously, there was a question asking me that I use the word obsolete for rebar. So I think that question I can respond now. So that one is So in most cases, so the fiber and fiber only segment works. There are certain cases when we have very high demand, high moment. So then we need to add some rebars and have a hybrid segment. And as previously explained, so there are procedure for analysis and design of those segments, which you can find it in the book I presented. So I think this is the way to go for fiber. So there are many other questions concerning the design of segment, which I cannot respond to all of them, but you can contact me through my email, or I can respond to all of them. These were all good questions and good attendance, and we really appreciate, and thanks to David and Charles also for attending, and you, Kristen, and Michaela for this session. I really enjoyed it myself.
It was a pleasure, Varia. David, Charles, do you have any specific message or any specific question that you think really needs to be answered?
I think there was a very last one, which I think was a very good question. The person is asking where we see the potential improvement for steel fiber reinforced segment design and usage. And I think what I would say is that fiber, you saw that we talked a lot about cracking and crack reef, and so fibers to work needs to crack, which means that the concrete is no longer linear, elastic, and the room for improvement is as we develop methods that are safe using the non-linear behavior, or the plasticity of the concrete, and we improve our design methods, which are a lot of them are still based on linear elastic solutions from the past. I think that we have a great potential there to improve design methods and guidance in that front, and take the bigger benefit of fibers.
Okay, thanks, David. Thank you, Charles. One final message from you.
Yeah, there's one question here. How do you ensure uniform fiber dispersion in SFRC during batching and mixing? Two answers to that. Number one, use fibers that are glued bundles, because you get a much better dispersion. If you start using loose fibers, they can bird's nest, as we call it, and you get a clump of fibers that will not break up. And the second important thing is to use a planetary pan mixer for mixing the concrete. This is a pan mixer with rotating arms that go in a planetary action, and they give you much better fiber distribution in the mix. So those are the only two things. Okay, so I'd like to thank everybody.
Thank you. Thank you. Well, unfortunately, we can't answer all the questions. As you can see, there are an enormous amount of questions. So it's obviously a topic that's raised a considerable amount of interest from our participants today. So thank you to everyone who attended today. We do hope that you enjoyed today's session. Don't hesitate to get in touch with ITATech to read the documents that were presented by our speakers today to learn more. And I would like to thank once again our sponsors, Amberg, Bouygues, Beckhardt and Heron Connect, for their generous support, which helps us to provide this lunchtime lecture series free of charge every month. Thank you again to Michaela, who helped organise today's session, for all her hard work. Just a quick word about our next session, which will take place on the 9th of September. We'll be taking a short break, over the summer. But we'll be back with you on the 9th of September, when we'll be teaming up with the ITA's Committee on Underground Space, ITACUS, and we'll be taking a fascinating look at how the underground can help power urban growth and climate resilience. So if you'd like to register for our next session, please log on to www.itaset.org and you'll be able to register. Finally, in a moment, a short evaluation form will pop up on your screens, and we'll be very grateful if you could take a couple of minutes to complete it, as your precious feedback helps us to continuously improve this lunchtime lecture series. So on that note, thank you again for having participated today, and a very big thank you to our three speakers who did a fantastic job, and we hope to see you all again soon. Bye-bye.
Thank you. Bye, everyone.